We will now return to our Boolean functions, and we will use our Boolean algebra in order to define most of the functions that we're going to see here. The first function that we have seen before is the AND function. The AND function gives output 1 if and only if both inputs are 1. And we're going to use this symbol to denote the gate in our circuit. Next we have the OR function, and the OR function will give us a 1 as output if and only if at least one of the inputs are 1. And this is a symbol that we're going to use as a gate in our circuit. Then we have the NOT function, or the complement, which gives the complement of the input. So this has only one input. These three functions are directly using the operations in our Boolean algebra that we have defined. Another function that is common that we can define is the NAND function, which is short for not AND. So this is the AND function and then with a complement. So this will take the output 0 if and only if both of the inputs are 1. So it's an AND function which is then inverted or complemented. And this is also seen in the symbol where we have an AND function, and then this circle here where we'll define the complement. Another function that we can define is the NOR function, which is short for not OR. And similar to the NAND function, this is the OR function but with a complement at the output. It will be defined as 1 if and only if both inputs are 0. And similar to the NAND function, we will use the OR gate here with an inverter represented by a circle in the output. Finally, the last function that we're going to define, which we cannot immediately define using our Boolean algebra, is the modulo 2 adder. And this will take the output 1 if and only if exactly one of the inputs is a 1. And here we're going to use this symbol to denote the XOR, or the modulo 2 addition, in our Boolean circuits. What we have seen here is 5 different Boolean functions that takes 2 variables as input and 1 variable as output. So now we can ask ourselves, how many different Boolean functions are there if we have, say, n variables? Well, with n variables, if we look at the number of rows in the truth table, this will be 2 to the n. So how many Boolean functions will there be? Well, with 2 to the n rows, and each of the row taking either a 1 or a 0 value, this means that we will have 2 to the 2 to the n different Boolean functions of n variables. We are going to define the following notation for Boolean functions. So let B be the set of the elements 0 and 1, and let these denote our Boolean values. Then B to the n will be an n-dimensional Boolean space with values 0 and 1 in each of the dimensions. B sub n will be the set of all the functions that we have from this n-dimensional Boolean space to the set consisting of 0 and 1. And B star sub n will be the set of all the functions from this n-dimensional Boolean space to the set consisting of 0, 1, and then we're going to add here a term that we're later going to call don't care. We're also going to define the inverse of a Boolean function. So the set of input combinations for which a Boolean function f gives the output 0 is going to be called the offset of the function. And we're going to denote this by f inverse of 0. And the set of input combination where it gives the output 1, we're going to call the onset of the function. And we'll denote this by f inverse of 1. And then the set of the input combination for which the function doesn't give anything of interest, in this case, so it will just give a hyphen, is going to be called the don't care set of the function. And we will write this as f inverse of this hyphen. So let us look at an example of this. So we're going to define our function f as a function in the set of all Boolean functions which takes input from the three-dimensional vector space and outputs either 0, 1 or don't care. And this is what we denoted by b star sub 3. So let us first define the onset of this function. The onset we denoted as f inverse of 1, and this is the set of all input combinations such that the output is 1. So this will be this input combination, this one, and the last one. So these input combinations we can write as 0, 0, 0, 0, 1, 0, 0, 1, 1, and 1, 1, 1. And in order to shorten this notation a little bit, what we're going to use is that we're going to use the corresponding integer which these combinations map to. So we're going to call this 0, 2, 3, and 7. And this is just for simplifying our notation. Our offset is defined as the input combinations such that our function is a 0, and we denoted this by f inverse of 0, and the set is given by this input combination here, 0, 0, 1, and the one that is defined as 1, 0, 0. So we have 0, 0, 1 and 1, 0, 0. So these are the two input combinations that will give us a 0. And then similarly, let us simplify this notation and write this as 1 and 4. And finally, our don't care set we defined as all the input combinations such that our output is the don't care. So these are the last two input combinations that we have. So it is 1, 0, 1 and 1, 1, 0. So it is 1, 0, 1 and 1, 1, 0. And again, let us simplify the notation, and here we write 5 and 6. So these are just different ways of defining the same function. So one way to define the function is by using the truth table. Another way to define the function is to use the onset, the offset, and the don't care set. And these sets can be written either in this notation, or we can write them in the little bit simplified notation which we used here. If we want to define the function, it is enough if we don't only give two of these sets. So if we give only the onset and the offset, then the rest will be the don't care set. Similar, if we give only the offset and the don't care set, the rest will be the onset. And of course, if we only give the onset and the don't care set, the rest will be the offset. So it is enough to uniquely specify the function by giving two of these sets.